We're going to look at some periodic trends among atoms. First of all is the size of the atom. Well, first we have to decide, how do you determine the size of an atom? Well, there's different ways to define it. You can look at the non-bonding atomic radius, which is also called the van der Waals radius. This is half the distance between adjacent nuclei in the atomic solid. And I'm not going to quiz you on these subtle differences between atomic size. I just want you to be aware that you can measure it in different ways. And that's what makes comparing things sometimes a little difficult. So here we have krypton, solid krypton, and if you look at the distance between one nucleus and the other and the next nucleus, and you divide that in half, we can say, okay, well, that's the radius of the atom. That's the van der Waals radius. We can also look at the bonding atomic radius, also known as the covalent radius. For nonmetals, that's going to be half the distance between two of the atoms that are bonded together. So bromine, we know, forms a diatomic molecule. So we're going to look at the distance between one bromine nucleus and another bromine nucleus in the molecule, and cut it in half and call that the atomic radius. Can you see that these might be a little different, right? And some of them, it's like, well, we can't really, krypton is hard to do a covalent radius on it because it forms so very few covalent compounds. It's really tough to do that. Bromine would be really hard to do a van der Waals radius on because it forms these diatomic molecules. And good luck getting a solid of bromine atoms. You can get a solid of bromine molecules, but it's not the same. And so we measure these differently for different things. In a metal, metals do not form covalent compounds for the most part. And so if we look at this bonding radius, we're looking at half the distance between two of the atoms that are next to each other in a crystal of the metal. So for a metal, that's going to be real similar to the van der Waals radius. What we're going to look at, we're just going to call it atomic radius, and it's sort of an average radius based on looking at that particular element in different compounds in different states. This is always going to be smaller, though, than the van der Waals radius because it includes some of those bonding radii. If we're looking at bond length, we're going to look at the sum of the atomic radii of the bonded atoms. That works for covalent bonds only. So this is how we try to get a grasp on the length of a bond and the size of an atom. So the trend goes like this. As we go down a group on the periodic table, the atomic radius increases. This makes sense. Now, what is this crazy graph? Here we're graphing the radius versus the atomic number. And so you might think, well, based on atomic number, as atomic number goes up, we've got more protons, more electrons, they should just get bigger and bigger and bigger, right? But when you graph it, you see this kind of a messy thing. This is not a straight line. There is a general trend that things are getting larger, but there's a lot of variation. So looking at going down a group, we're going to compare elements that are in the same group. So lithium, sodium, potassium, rubidium, cesium. These are all in group 1A. And so as we go down the periodic table, we see that the size of the atom gets larger, and that makes sense. We can also look at the other end, the noble gases. And as the noble gases go down in the periodic table, they get larger. It's not a linear relationship, but there is a trend. And if you look at group 2, this is group 2, we see that same trend. Oops. If we look across a period, from left to right across the periodic table, we might expect that the radius would also be getting larger because we're adding electrons, right? That makes sense. But it's not right, though. As we go across a group or across a period in the periodic table, the atomic size goes down. This is a graph showing size. So if we look, let's just stick with the top one here, the second period. Lithium has a radius of 152, beryllium's 112, 85, 77. It's getting smaller, and there's some little glitches in here, but the overall trend is getting smaller. Doesn't really make sense on the surface. What's going on? Well, it has to do with shielding. There are interactions between the electrons in an atom, and those interactions cause differences in sizes. So we've got electrons that are being attracted to the nucleus, and they're being repelled by each other. Opposite charges, positive nucleus, negative electron, attract. Two electrons, though, repel each other. And so we have this balance of conflicting attractions and repulsions. What happens is that the outer electrons get shielded from the nucleus by the core electrons. And that shielding causes the outer electrons to not experience the full charge of the nucleus. Because they're experiencing a lesser charge, they're not as attracted to the nucleus. So here's an illustration of shielding. So this is lithium. Lithium has 3 protons in its nucleus. It has 2 core electrons, the 1s electrons, and then it has 1 valence electron. So the core electrons in the 1s orbital are closer to the nucleus than the valence electron is in the 2s orbital. And these are broad generalizations we're talking about. So when this electron looks through this cloud at the nucleus, these 2 core electrons partially offset the charge that it sees. And so it experiences less of an effective nuclear charge. So this is attracted, really the effective nuclear charge then is approximately 1 instead of 2. I had this analogy that popped into my head over the weekend, and then it kind of went away, so I'm going to have to make one up again. If you think about getting in line to get something nice, what would we be getting in line for? Maybe they're handing out free donuts. I don't know if this is going to work or not. These 2 guys are ahead of the valence electron. And so they each get a donut first, and so when this guy gets there, there's only 1 donut left. The attraction for the 1 donut is less than the attraction for 3 donuts. Does that work at all? Not really. I'll have to fix that. Anyway. Yes?
So like somebody doing a mob and the person on the outside trying to get in?
Yeah, maybe so. So maybe there's like some famous person that you want to get their autograph or you want to see, and there's this mob around them, and so you can't even really get close, and so you may just kind of give up. The attraction is not as great as if there was nothing between you and the person. I think that's better than the donuts. I need to work on that one. The problem is I make up these analogies, and then sometimes I forget them, because I haven't taught this class for a year. It was last fall. That was a long time ago. So much stuff has happened. It's gone. The analogy's gone. So when we talk about effective nuclear charge, the simple way to estimate it is you take the actual charge on the nucleus. That's the number of protons. Z is the atomic number. It's the number of protons. And you subtract the core electrons. So we learned to look at the electron configuration and identify core electrons and valence electrons. Now, there is a little bit of shielding among the valence electrons, but it's small enough that we can just ignore it. So let's look at nitrogen and argon and figure out what are the effective nuclear charges of those 2 elements. Well, let's do nitrogen first. What is, we'll look at Z effective. What's the charge on the nitrogen nucleus? What's the atomic number? 7, right? Yeah, 7. How many core electrons? Well, that's kind of a tricky question. It's easier to ask yourself, how many valence electrons does nitrogen have? Well, what group is it in? 5. It has 5 valence electrons. 2 is the correct answer to how many core electrons. Has 5 valence electrons. We can tell that by the group number on the periodic table. So 5 valence electrons, 7 total electrons, then it must have 2 core electrons. So I'm going to subtract the 2 core electrons, and I'm going to end up with an effective nuclear charge of 5. Okay, that's nice. Let's look at argon. How many electrons, or I'm sorry, what's the atomic number of argon? 18. So argon has 18 electrons, 18 protons. How many valence electrons does argon have? What group is it in? It's in group 8. So it has 8 valence electrons. If it has 8 valence electrons, all the other electrons are core electrons. So it must have 10 core electrons. So its effective nuclear charge is 8. That means that those valence electrons for nitrogen are going to see a charge of 5. The valence electrons for argon are going to see a charge of 8. Do we have Coulomb's law on this next? No. So, do you remember Coulomb's law? The energy is proportional to charge 1 times charge 2 divided by the radius. So if we have our 1 electron experiencing a plus 5 charge versus our minus 1 electron experiencing a plus 8 charge, there's a stronger attraction for the plus 8 effective nuclear charge. When we look as we're going in the same group, we're increasing in size. What am I doing? This is transition metals. I don't want to talk about them. I feel like that, oh, there. I don't know what I'm doing. Just shoot me now. There we go. Okay, so when we go down a column, what we observe is that the principal quantum number of the valence electrons increases. So if we compare lithium and sodium and potassium, the valence electrons are in a higher energy level. As the principal quantum number increases, the size of those orbitals increases, right? So it makes sense if you've got electrons in the 4s orbital versus the 2s orbital, that atom's going to be larger. Does that make sense? When we go across, though, the effective nuclear charge is increasing, but the principal quantum number is the same. This gives us a stronger attraction between the valence electrons and the nucleus, and thus we get a smaller atom. So we looked at, let's look at sodium and argon. So we already figured out for argon that the effective nuclear charge was 8, right? Z effective equals 8. What's the effective nuclear charge for sodium? Well, how many electrons does sodium have? 11. So Z is 11, and how many core electrons are there? 10. So the effective nuclear charge for sodium is 1. That valence electron, though, is in the 3rd principal level, roughly the same distance from the nucleus. Sodium's valence electron experiences a charge of plus 1. Argon's experiences a charge of plus 8. Which one is going to be more strongly attracted to the nucleus? We've got an electron. So if we think of this as this effective charge as being Q2, and here we have our 1 electron with Q1, and over here we have our one electron we're comparing, and the effective nuclear charge, Q2, is going to be 8. Which is more strongly attracted, the 1 electron to the +1 charge or this electron to the +8 charge? The +8, right? Coulomb's law says the attraction is proportional to the charges of those two objects. So this would be 1 times 1. This is 1 times 8. The attraction is 8 times larger. What that does is it pulls the outer electrons in farther. As we go across the period, we're filling up the same principal level, but the effective nuclear charge is increasing. So as we go across the periodic table, it's being squeezed in. They're coming in closer. Does that make sense? I got some nods, that's good. The transition metals, they're kind of squirrely. They don't follow as nice patterns as the main group. We still see them increasing in size as we go down a group, but going across, there's very little difference, much less difference than we see in the main group elements. And a lot of that has to do with the valence shell is the NS2. Across a period for the transition metals, what we're filling up is the d orbitals. The d orbitals are not a valence shell. Those are core electrons. And so we're seeing the valence shell being the same. The effective nuclear charge is approximately the same. And so there's very little difference. Let's just go back to that graph. Well, here's the table. So the differences in here are much smaller than what we see going across with the main group elements. If we look at the graph, these are here's the transition metals. And there's a trend here, but it's not real definite, and the changes are pretty small. Here's the main group going from potassium to krypton. There's big changes going on here. The transition metals, not so much. They're much harder to predict. Okay, so based on periodic trends, choose the larger atom. Tin or iodine? Well, we have to look at the periodic table. So for tin is over here, and then we've got, I really should have a periodic table in here. We've got 2 elements, and then we've got iodine. These guys are in the same period. Which one's larger?
In radius or?
In radius. Atomic size. The tin is larger. Because as we go across, effective nuclear charge increases, and those electrons get pulled in, and the atoms get smaller. So tin is larger. Germanium or polonium? Germanium would be here. Polonium's down there. This one's tough. We've got opposing trends. If we look at going across, we expect polonium to be smaller because it's to the right of germanium. But if we look at the trend going down, we expect polonium to be larger. So this one's like, which trend is more important? Well, usually the up and down trend is more important because polonium's valence electrons are in the 6s and germanium is 4s. The higher principal level is going to be larger. Yes?
So in 101B, Mr. Reed,
Mm-hmm.
he said that the more number of protons, the smaller the atomic radius. That's one related because the attraction of the protons to the electrons.
Yes, as you're going across. So more protons in the nucleus is going to give you more effective nuclear charge. Yeah, but that doesn't work going down. Because as you're going down, the electrons are in larger and larger levels, right? 6s versus 4s. The sixth energy level is further from the nucleus than the fourth energy level. And the distance is a big factor in the attraction. You think about a magnet, right, on the refrigerator, and you stick one piece of paper up with the magnet. And then you do 2 pieces of paper and 3 pieces of paper. Eventually, you're going to get to a point where just adding one more piece of paper, the magnet's not going to stick. Tiny distance difference makes a big effect in the attraction, right? So for these guys, this is what I would consider a tricky question on an exam. I might throw one in there because 1A is all about giving you tricky questions on an exam. But I would consider this tricky because you've got opposing trends. So I'd put my bet on polonium being larger. How about chromium or tungsten? So if we just look at a smidgen of the periodic table, we see that chromium and tungsten are in the same group. Which one's larger? Tungsten. Because chromium's valence electrons are in the 4th level, and tungsten is in the 6th. They're going to have about the same effective nuclear charge. But because they're in a larger principal shell, they're going to be farther from the nucleus, the atom will be larger. Any questions? If you can think about what's going on, then you can reason this out. And that generally works better, especially on an exam. Exams are stressful. You know, you come in, you've studied, and you look at the first question, and your brain goes blank, right? Does that happen to you? That used to happen to me all the time. So then all the rote memorization things just vanished. And now you're just left with thinking about stuff, figuring it out from scratch, right? So if you can think about what's going on here, you can wiggle your way out of it and still get the answer right on the exam. If you're memorizing a trend, which is okay, if you're just memorizing a trend, when your mind goes blank, then you're kind of sunk.